All right, our lesson today is going to be on asymptotes, but we're going to start off by reviewing what we did in the previous unit. So I need you to get a graphing calculator because you're going to follow along. Together we're going to indicate all horizontal and vertical asymptotes and what you know about log and exponential functions. So we're going to start off. Logarithmic functions have a vertical asymptote. Exponential functions have a horizontal asymptote. So a vertical asymptote is going to be a line straight up and down. Horizontal asymptote goes straight across left and right. So let's take a look at our very first problem. Y equals log parentheses x minus 2. Go ahead and put that in your calculator and don't forget the parentheses. Okay, so you're going to notice that the vertical asymptote is x is equal to 2. This is a log. We said down here that logs have vertical asymptotes. Now I've graphed this for you down here. So if you take a look, there's no horizontal asymptote. And I'm going to get you a picture in just a second. When you look at this second one, this is on your calculator too. This is the natural log. Y is equal to the natural log and of this quantity x plus 3. Put it in parentheses. Natural logs follow logarithms, so you're going to have a vertical asymptote, therefore no horizontal asymptote. What do you think the vertical asymptote is going to be? X is equal to negative 3. This last function, we have an exponent here with a variable, so this is your exponential. Exponential, according to our notes, has a horizontal asymptote, but not a vertical asymptote. So the horizontal asymptote is y is equal to 3. All right, so take a look at this graph right here. When you graph it on your calculator, you should get y equals log quantity x minus 2 should have a vertical asymptote. So this graph does not pass by this line right here, and this line is x is equal to 2. So take a look at it on the graph. All your x values here are 2. Take a look at this second one. We also have a vertical asymptote right here. This graph, natural log of x plus 3, does not cross past this line. X is equal to negative 3. It stops. Okay. Take a look at this last one. This is your exponential. It comes down from left to right, and then it kind of tapers off. And there is a horizontal asymptote. So that's the review. Now, if you take a look, the parent function of log of x minus 2 is just log of x. So, did you notice that this is x minus 2 and the vertical asymptote is x equals 2? Did you notice that this is x plus 3 and the vertical asymptote is x is equal to negative 3? Now, those were inside parentheses, and those are your vertical asymptotes. This one is not in parentheses. Outside parentheses is going to give you your horizontal asymptote. So, in our lesson today, we're going to be studying rational functions, asymptotes, along with a lot of other properties. So I'm giving you these functions right here and these graphs, and what I want you to do is I want you to graph them on your calculator. Now I have a picture here of what you can do to graph it on your calculator. Go ahead and hit the alpha button on your calculator. It's on the left. Then hit y equals and hit enter. What will happen, it'll bring up a fraction so that you can go ahead and put these in the calculator and graph them. So I'm going to give you a chance to do that. And then you can show it to me in your booklet at a later time. Here we go. So what we're going to do now, we have this graph here, and we're going to analyze the graph. We can see that this graph, you see the arrows right here, this graph is coming close to this line, but it's not crossing this line. What does that tell us? That tells us that this is an asymptote. Here, when we look at this part of the graph, this graph is actually getting close to this line, not passing it, coming up, getting close to this line and not passing it. So again, it is an asymptote as well. These type of functions are called rational. Rational, you see the word ratio. So we're going to have a numerator and a denominator. The parent function is 1 over x. If you want to graph that, you'll see the parent function. Anything else would possibly be a shift. Shift to the right, shift to the left, shift up, or possibly shift down. Here is a vertical asymptote. What is the equation of this line? Hopefully you said x is equal to 2. Vertical lines go up and down. Find the point that it goes through, and that's the equation of your line. X is equal to 2. Here, this line, here's our vertical asymptote. Excuse me, horizontal asymptote. And the horizontal asymptote is at y is equal to 1. Notice in this graph, there is a hole. There is an opening here. What is the location of that hole? Well, if I go over 3 and up 2, I found the location of the hole. We call that a point of discontinuity. What is an asymptote? We talked about it in the last unit, but we're going to expound upon it in this unit and do more practice with it. An asymptote is a line that a graph closely approaches but does not touch across that graph as it goes to positive or negative infinity. Transformed equations without the hole considered. Y is equal to 1 over x minus 2 plus 1. So if you take a look, notice that here in the denominator we have x minus 2. When we talked about transformations, we always talked about the opposite. So we expect this to move 2 units in which direction? 2 units to the right and 1 unit up. So get ready, get ready. It is a lot in this lesson, so let me tell you some of the basics that we're going to have to think about in every problem. We are going to have to think about factoring. Some of them may need factoring and some of them will not, but guess what? We got to consider it. We're definitely going to be simplifying. We're going to be substituting a value back in. Not all the time, but we definitely got to consider it. And the last thing I want you to consider is circling the highest exponent in the numerator and the highest power or exponent in the denominator. We're going to compare that. And basically, we're going to be looking for the degree of the polynomial, or excuse me, the degree of the function. So for a rational function, we will have a hole occur when a factor can be canceled from the numerator and the denominator. So if I have this function here and I see x plus 3 at the top and I see that same expression at the bottom, I can cancel it out. That is an indication when you can cancel. It's an indication that there's a hole in the graph. We always take that expression, which in this case is x plus 3. We set it equal to 0 and we solve for x. There is a hole in this graph at x is equal to negative 3. Well, we actually need to know the location, the exact location. So we're going to plug in x equals negative 3 into our simplified expression. And we're going to find out what our y value is. So 1 over negative 3 minus 5 gives me 1 over negative 8. So the hole in this graph is going to be at negative 3, comma, negative 1/8. Let's talk about vertical asymptotes. Vertical asymptotes, those are your vertical lines that your graph will not cross. So the vertical asymptotes, again, we have to simplify. We're going to factor and we're going to simplify. Once we've done that, we are going to set the denominator equal to 0. In the case of the one that we started on this slide, 1 over x minus 5, set the denominator equal to 0. So when I set the denominator equal to 0, I find out that x is equal to 5. So that's where my vertical line will be at x equals 5. We have a little bit more to do with the horizontal asymptotes. We have to consider the degree of the function. On the previous slide, I said just circle the highest exponent at the top and the highest exponent at the bottom. We're comparing the degrees. So if you notice that the degree of the top is less than the degree at the bottom, that means the bottom is bigger, then our horizontal asymptote will always be y equals 0. So bottom bigger, y is 0. If we find out that the degree of the top is the same as the degree of the bottom, we are going to write a ratio. And the ratio is going to be the leading coefficient of the numerator over the leading coefficient over the denominator of the denominator. So here we have y equals 2x to the third power plus 7x minus 1 over 5x cubed plus 4. Let's consider the degree. The highest power here is 3. The highest power here is 3. They are equal. So I want to take a look at the leading coefficient at the top, which is 2. At the bottom is 5. So our horizontal asymptote is 2 over 5. Properties of rational functions. Here we are. We are given this function. There is a hole in the graph. How do we know that? Because when we look over here at the graph, we can see the hole. Unfortunately, when you graph this using your calculator, it will not show you the hole. So we need to be able to do that algebraically. What do? Factor x squared minus 3x minus 4 factors out to x minus 4 times x plus 1. Now we see common factors. What does that indicate? It indicates there's a hole. When a factor cancels from the numerator to the denominator, there is a hole. We find out what the hole is by setting the factor equal to 0 and solving. There's a hole at x equals 4. Let's plug it back into our simplified problem and let's see what we get out for y. 4 plus 1 is 5. The hole is at the place 4, 5, which is consistent with the picture of the graph. So when we look at our x values that make the function true, we can see we can't have x equaling 4, or we'll have division by 0. So the domain, x can be all real numbers, but x cannot equal 4. Let's take a look at the range, the y values. As we look at the y values can be any y value, but y cannot be 5. So given the function y is equal to 1 over x plus 3, here's the graph, and you could graph it in your calculator to verify. What do you see here? This is a vertical asymptote. Where is it? Set x equals -3. Why? Because we set the denominator equal to 0 and x is equal to -3. What is that again when the denominator is equal to 0? It is a vertical asymptote. We see another split in this graph, and it's going right through here, represented by this green line, and that is y is equal to 0. Well, we notice that the degree at the bottom is bigger, and when the bottom is bigger, y is equal to 0. If you want to take a look at the powers, anytime you have a number here and you want to put a variable with it, as long as the variable is x to the 0, this is still 1. So technically the bottom power is bigger because x to the first power is x, but x to the 0 power is 1. So the bottom is still bigger. So we can take this, figure out what the domain is. If we have a vertical asymptote, that'll help us with the domain. X cannot equal -3. Here, horizontal asymptote will help us with the range. Y cannot equal 0. All right, here we go. Given a function, y is equal to 2x plus 5 over x minus 3. Here's the graph here. Graph it in your calculator. Follow along. Get practice. The graph splits here. What is that vertical asymptote? Well, this point right here is 3, so x is equal to 3. That is a vertical asymptote. How did you get that? You set the denominator equal to 0. Here we have a split in the graph. This line going across is a horizontal asymptote. Where's that horizontal asymptote? It's at y is equal to 2. Let's check out the powers. Okay, the power here is 1. So the degree is 1 at the top and the degree is 1 at the bottom. When the degrees are equal, we use the ratio of the leading coefficient. So that's 2 over 1. So that would explain horizontal asymptote. Next, given this function here, if you haven't noticed, they're getting progressively more difficult. Given this function here, and we could definitely put in the calculator, we would see everything, but the calculator will not show us the whole. So looking at this though, we can see that there's a hole at -3 from the picture here on the screen. What do we need to do? Let's factor. So we factor x squared plus 5x plus 6. You always want to check your loops too. And so if I factor and I get x plus 3 and x plus 2. And you want to check your loops because it's easy to mix up the factors. So this inner loop gives me 3x. And this outer loop gives me 2x. And 3x and 2x gives me 5, which is my middle term at the top. So I'm looking good. At the bottom, there's a GCF. Always pull out your GCF first. And then I get x squared plus 2x minus 3. Can I factor that? Absolutely. So when I factor that, check my loops. Here I have 3x. And then I have -x here with my bottom loop. And that comes up to 2x, which is my middle term right here. So I'm looking good. I can cancel from top to bottom. That means there's a hole. So I take that factor, x plus 3, and set it equal to 0 back here at the top. So I have a hole at x equals -3, but I need the y value. Plug it back in, follow along, and I get y is equal to 1/8. So here's the hole here at -3 and 1/8. Vertical asymptote, I set the denominator equal to 0. I canceled out x plus 3, so that's not a part of my denominator anymore. What's a part of my denominator is 2 times x minus 1. I divide both sides by 2, and I get x minus 1 is equal to 0. So I get x is equal to 1. Vertical asymptote. Check out the picture over here. That is x is equal to 1. Horizontal asymptote. Check the powers. Powers are the same. So it's 1/2. So check out my horizontal line in the graph. It is y is equal to 1/2. Awesome. Once you've done this and you've finished, go ahead and grab your homework sheet, and you should be able to analyze the graphs and be able to identify horizontal asymptotes, vertical asymptotes, and any holes. Good luck.